ways of imaging the brain. Until the middle part of the 20th century, what little was known about the brain consisted of a melange of speculation and dogmatism based on hosts of hoary old men staring through microscopes at brightly colored dye-stained neurons. Thanks to advances in brain imaging techniques over the last 30-plus years, it's currently possible for neuroscientists, many of whom are now women, to observe the development of the brain in real time, and without any need for either speculation or dogmatism. The principle behind these illuminating, in both senses of the term, imaging techniques is straightforward. Blood flow to the brain varies with activity. The greater the activity, the greater the flow of blood needed to replenish the oxygen and glucose used by the active neurons. This isn't any different from what happens elsewhere in the body. When you lift a 100-pound barbell at the health club in an effort to attract the attention of someone nearby in whom you're romantically interested, blood flow increases in the muscles of your arms and chest based on the increased need by those muscles for oxygen and glucose. Similarly, when you use a specific circuit in the brain, the components of that circuit will become more active and call on the circulatory system to provide additional glucose and oxygen. Positron emission tomography, PET, and functional magnetic resonance imaging, fMRI, detect the changes in blood flow within active parts of the brain and record them while the subject lies within a special scanner. Thanks to fMRI imaging and other techniques, we know that the brain never wears out. It gets better the more we use it. It changes in structure and function throughout our lives. As a consequence of this plasticity, we sculpt our brains according to our life experiences. As a result, no two brains are exactly alike, not even the brains of identical twins who, while they share the same genetic makeup, don't share identical experiences. Due to this diversity in the brain's organization and structure from one person to another, it's often possible to reach valid conclusions about a person on the basis of his brain's organization. For instance, while looking at an fMRI, a trained observer can distinguish the brain of a skilled pianist from that of a non-pianist. That trained observer will note that the pianist's brain shows increased activation in the finger areas of the motor cortex while she listens to a piano concerto. The same thing happens if she just watches someone playing any musical composition on the piano. But it won't happen if she observes that person merely making random finger movements on the keyboard. Under these circumstances, the pianist's brain responses won't differ from those of a person with no special musical expertise or interest. A similar specialization occurs in dancers. A ballet dancer will show greater brain activation while he watches other ballet dancers perform. This won't happen if he watches ballroom dancers. Nor is brain specialization limited to the arts. If that pianist, at the conclusion of her performance, takes a cab from the concert hall to her apartment, her cab driver's brain is likely to have an enlarged hippocampus, a brain area heavily involved in spatial visualization and navigation. The same is true for any specialized occupation. A surgeon will show greater activation in the hand area of the motor and sensory cortex than will a doctor who doesn't perform surgery. The pianist, the ballet dancer, the taxi driver, and the surgeon have shaped their brains by virtue of their experiences. The same thing is true for all of us. We create new patterns of neuronal organization according to what we see, what we do, what we imagine, and most of all, what we learn. Learning something new involves establishing a pathway within the brain made up of millions of brain cells. As we learn more, these pathways increase in complexity, a process similar to the branching of a tree as it grows. Thanks to its plasticity, the brain can be thought of as a tree of knowledge. When in full bloom, a tree blossoms. Roots give off branches, twigs, and leaves. Similarly, learning increases interaction within the brain with more and more other neurons establishing fuller and richer circuits. But if learning stops, the brain, like a tree losing the luxuriant structure seen at full bloom, reverts to a state corresponding to that of a tree in winter. You can picture human brain development as a continuum, ranging from infant child to adolescent to adult, and finally to the mature older brain. Each stage of development